Next speaker is Matteo Demuru from Aix-Marseille University, and he will be talking about electrographic intraoperative biomarkers for epilepsy surgery. Matteo, please go ahead.
Can you hear me?
Yes.
Yeah. Okay, so I'll go. And can you see my screen? Yeah.
Yes. Also, sorry. Yes. Sorry.
Okay.
I am muted. Okay.
Okay. Sorry. Okay. Good morning, everyone, and thanks for the invite. As you can see, I put non-invasive in quotes because I'm going to talk about some invasive methods. But I hope because let's say functional connectivity will be overall my presentation.
Yeah,
so
we can still accept you.
Yeah. Thank you. So I thanks also Giovanni for the presentation. So that set a little bit the frame for me, but I need to, tell something more about epilepsy just to, set properly the framework of my presentation. So as Giovanni said, also there are some patients that are drug resistant to the medication, and for these patients, sometimes surgery is if some criteria are met, is a viable option in order to be cured, to be seizure free. And what is the goal of epilepsy surgery? The goal of epilepsy surgery is to find and remove what is called the epileptogenic zone. That is the area in some way that is deemed to be responsible for ignite the seizures. Nowadays, we have more, let's say, a holistic view of epilepsy. It's not just, something that is, there is one responsible, but it's like there is more a network view. So as epilepsy is a network disease, so it's like the interaction of different areas. And functional connectivity in some way, and brain signal analysis, brain network analysis, like can help into, disclosing this network view. So I'm gonna talk during this presentation about I'm gonna present you the results of a recent paper I had the opportunity to do with my experience during the postdoc in the Netherlands. I was working in Utrecht in the hospital, and we managed, let's say, to assess two things, more or less. One, I tried to present the results of the functional connectivity method, but more in general, signal analysis method from intracranial recording, intraoperative recording. And what we try to assess is like if this method can really bring something that can be used into the clinic. So literally, we try to assess if they work for individual level. And another example that I'm going to talk in the end is like the virtual rejection. So if there is a possibility to simulate in advance the rejection in order to plan it, to choose the best strategy. So in order to give you a proper understanding of the type of data I'm using, I need to explain a little bit how epilepsy surgery is done, at least how it's done in Utrecht, and with the help of the electrocorticography with ECO. So the idea is like once the surgeon open the skull and expose the cortex, a series of recordings, you can see the grid in here that is with all the electrode that is moved around in order to record from different locations. And then, the surgery begins. So the surgeon starts to remove some part of the brain, like for example, in this situation too. And what happened? It is an iterative process. Every time there are recordings, then the neurophysiologist assess the data like live in the operation theater, and it tries to say if there is some kind of abnormal activity or not. If that is the case, he suggests to the surgeon, okay, probably it's better to remove a little bit more. But eventually, the surgery stops, and so the surgeon doesn't touch anymore the brain, and there is another set of recordings also there. So you have, let's say, pre-resection recording and post-resection recording. And during my talk, I'm going to talk about these two sessions. So when the surgeon doesn't touch the brain, so before to touch anything, and after the surgery is done. So after the removal of the epileptogenic, of what was the hypothesis of the epileptogenic zone, so the cortex is removed. So another information that we have on the electrode is like, we can, if we align the picture, we can say what was resected, which are the electrodes that were resected in the pre-resection period. So we have a label for each electrode, if it was resected or not. So what did we do? So because if you start to look at all the literature about functional connectivity for localization of the epileptogenic zone, it's like, it's like a mare magnum of, let's say, data analysis techniques. There are really a lot. And sometimes even there are even contradicting results. What we try to do is like, we try to be to choose some of the methods in order to be kind of exhaustive in terms of univariate method, bivariate method, and multivariate method. And the idea was like to choose for all this kind of categories at least one method that showed some significant results in terms of the localization of the epileptogenic zone. In terms of, let's say, univariate, where we chose autoregressive residual modulation, phase amplitude coupling, or bivariate, like phase locking values, phase like index, and nonlinear correlation index, or multivariate, Granger causality and directed transfer function. Of course, these are not the only ones that are there, but the criteria we chose is like if we saw something in intracranial recording that shows some localization significance in terms of localization for the epileptogenic zone, we took that measure and we assessed them. So the novelty, let's say, of the work we did was like that for the, so it's like rare to have both pre-resection recording and post-resection recording. And we, use the post-resection recording in order to build a ground truth, a reference. So the idea for us, like, we had patients that were seizure-free without medication after the operation. And the idea was like, can we use these patients in order to build some kind of reference of some normative value for our biomarker, meaning that if the patients are seizure-free, it means that, the epileptogenic zone was removed, and what's left is like normal tissue. And if we record and sample the normal tissue, we can compute some reference for our biomarker. And the idea is like we compare that reference with the value in the pre-resection in what was resected. So if a biomarker is sensitive to the epileptogenicity, it should be higher compared to the normal value in the post-resection in the cured patient. And this is what we did. We select like 47 patients, 30 temporal and 17 extratemporal. One of the conditions was like we should have at least 1 minute pre-resection recording and 1 minute post-resection recording. We tried different montage, and the pipeline, I won't enter into the detail, but are the classical pipeline that are used usually for functional connectivity. And we use as a statistic, if we had a univariate measure, just the average for each channel across time. And if we had a bivariate or multivariate, from the connectivity matrix, we compare a statistic for each channel, looking at the strength, if the measure was not directional, or the out strength, if the measure was directional. And these are the results of the 7 biomarkers we analyzed. So out of 7, we could find that there is a group effect in comparing the pre-resection resected data versus the post-resection data in cured patients in 5 out of 7 biomarkers. So for 5 biomarkers, we could find a significant, so they were able to detect an effect. So if they were able in some way to find a difference between what was in the pre-resection resected data and no. We continue using this kind of approach to look not just at the group level effect, but now we try to summarize for each patient. We look at the maximum value we could compute in the pre-resection resected data, and also in the post-resection data, with the idea that, when there is a resection, usually we didn't want to be biased by the amount of brain that was resected, because the idea is like that when they do some resection, usually inside the resection area there is also healthy tissue, and we didn't want to be biased by that, so we choose to select for each patient just the maximum. And then when we did that, out of the 5, just we could find significant results for the phase 2 coupling. And eventually we tried to investigate if there was the possibility to define a threshold in order to discriminate between, let's say, pathological tissue and not pathological tissue. So, and we used the threshold for each biomarker as the maximum value in the cured patient in the post-resection. So if a patient has a value that is higher than that, it means that we could localize the epileptogenic zone. And this was true for the best result we could have was like for 17 patients out of 47. That is not a great result. We tried to, pull together all the biomarkers, and I mean a cumulative biomarker, saying that if at least one of the biomarkers was higher than the threshold we set, then we could localize it. And when we did that, we improved a little bit the numbers. So from 17, we passed through 23 patients for whom we could find the epileptogenic zone, but it's like still it's a poor result. Then we try to split our data. So looking at the different kind of pathology they have, let's say the epilepsy type, they were temporal or extratemporal, and it happened that in the temporal patient we could find that almost for every patient we could localize the epileptogenic zone, and that was not true for the extratemporal patients. So what have we learned from this assessment? That we could replicate, let's say, the result in the literature for some of our biomarkers, so we can find a group effect. Phase amplitude coupling show the best performance as a standalone measure, and combining the biomarker helps, and also the epilepsy, the type of epilepsy matters in this kind of analysis. I continue just explain to you the last result we had with our virtual rejection approach. That is kind of the idea was like to have an operational tool that can help to delineate the epileptogenic zone and plan the optimal rejection surgery. So the idea was like to act on the functional connectivity matrix and see if we could, using that information, kind of simulate the real rejection. So if we can match the real rejection. Again, we could do that because we have pre-rejection recording and post-rejection recording. So the idea was like to select a certain kind of patient for which we had more or less the grid that was placed in the same in the same location during the pre-rejection recording and in the post-rejection recording. And the other criteria was like that what was resected, that you can see in here highlighted in green, should be within the rejection, the recording grid, with the idea that whatever we can compute here and simulate using pre-rejection data, we had the ground truth that we could see really that if we recompute that in the actual data, so removing what really was removed, we can match the result. So, and we applied two kind of virtual rejection. One that I called naive, and the other is called the partialization. The naive approach is like once you have the signal, you compute the connectivity matrix, and from the connectivity matrix, we act on that. We remove all the channels that were really rejected, and as a statistic, then we take the average of the connectivity matrix, so a global measure. With the partialization approach, what we did is like, other than acting directly on the connectivity matrix, we act on the signal. So first, we remove, for example, in this case, this signal, and we regress out the contribution of this signal in all the other signals. So in some way, we partialize all the other signals, and then we compute the functional connectivity on what's left. And eventually, as a global statistic, we take the average of that matrix. So we tested two things. If the global connectivity after virtual resection, after both, resemble the actual post-resection after the global connectivity after the actual resection. And the second thing that we assessed was like if there was an overall effect between a pre-resection recording and post-resection recording. We investigated if we could detect that effect between pre-resection and our virtual resection. So we used 11 patients, extratemporal patients with the criteria that I said. We computed a functional connectivity measure and nonlinear index called H-square with 5 overlapping windows and a common montage. And this is like kind of an idea for one patient of results where we have like 4 distribution, as I said. We have the real pre-resection data, the post-resection data, and the data with the virtual, when we apply virtual resection. In here, in each violin plot, each dot is like a global connectivity, meaning the average across the matrix for each time window, okay? So the first thing that we tried to assess was if the conductivity in the blue resembled the real one, so the virtual resection mimicking the real resection, so remove it was the electrodes that were really removed. Can we find the same kind of, can we predict the post-resection global connectivity? And the second question we asked, if there was a relationship, let's say a significant difference between these two, so with the pre-resection versus post-resection, can we find the same effect between pre-resection and virtual resection? These were the two questions we had for each patient. And the results were like, for what concerned the prediction, so if we can, from our virtual resection, match the post-resection values, we couldn't. For each two of the, let's say, virtual resection, we couldn't match for any of the patient. While regarding detecting an effect, so if there was an effect between pre versus post, we could find that the partialization approach, where so we regress out every channel, we could find that in 7 out of 8 patients, we could in some way detect the same effect. And I said 7 out of 8 because we defined even an applicability criteria for our method that in the pre-resection data, we should at least have some minimal level of connectivity in order to apply. So this is like an a priori criteria for the applicability. So what have we learned from the virtualization approach? That it's really complicated to match, from pre-resection data, what really happened after the resection. And the partialization approach probably is better than naive. But still, we have like 11 patients. So more patients are needed, if you want, in order to, investigate better the problem. And I think we are still far from a clinical translation. So these tools for now cannot really be used into the operation theater. And I thank all my collaborators during my postdoc in the Netherlands, so Michael Zalman specifically, and Cillian Kalinski. I thank you all. And if there are some questions, please don't hesitate.
Okay, thank you, Matteo. Thank you very much. Very, very interesting. Let me see if there are questions from the audience. We have one question from Sarah.
Hi, thank you very much for your beautiful talk. I have a quite technical question. I may have lost it, but when you show in the first part of your talk, you have shown the picture of the violin plots. I missed what was on the Y lab when you were comparing the different metrics. I missed what was on the Y lab.
This one?
Yeah, exactly this one. Because, okay,
This
I have read exactly.
Okay, so in here is like for every biomarker we use. So the idea was like, because we are looking at the problem is like to locate the epileptogenic zone. Specifically, what means like if we can find the channels that are, let's say, to be considered pathological, okay? And the idea is like we have a measure for each channel, okay? And so, for example, in here, if depending of the type of measure, if it is univariate, bivariate, or multivariate, we have on the y-axis, for example, for the univariate measure, you have just that measure that is average across time for that channel, while for the others, for example, let's say PLV, the like phase lock-in value, because you end up, when you compute a connectivity matrix, so you have a matrix, and in order to summarize for a channel-based number, we need to compute something, and we decided to compute like the strength, so averaging across the column of the matrix in order to have what in graph theory is called the node strength, more or less, for each channel, and that was that.
Okay,
and,
so you did some sort of seed-based, where the seed is the channel, and then you compute you summarize the information with respect to the others.
Yeah.
Okay.
Because the things that we want to know is that channel, so we want to be local. So the idea was like, which are the question usually in epilepsy surgery is like, which channel I have to remove? So which, not channel, but the area that, let's say, cortex beneath the channel that you need to remove, which is in some way pathological.
And does it have any sense to do something similar, but at the source level? Even though I understood you are using ECOG,
no, actually,
less.
no, but actually, this is like it's really interesting, this question, because what you miss with ECOG actually, because okay, you are recording on top of the cortex, but sometimes, especially if depending on the type of epilepsy, the source is not on the cortex, so you don't have, other than there is some malformation stuff. So sometimes, let's say, the source is like more deep, and that is in some way a problem that because you have, let's say, the same kind of problem that we have in MG. So you cannot really pinpoint because it is deep in some way, even though this kind of analysis, usually when they do that, usually now they are doing they are doing ECOG, but also they put an ACG in electro, so a stereo electro, in order to investigate better that.
Okay, thank you very much.
There's a question by Gabriele Arnulfo. Gabriel, you can unmute yourself if you want to ask it.
Thank you very much, and thank you for Matteo for the nice talk. I was just wondering what, because it's basically electrocorticography as far as I understood. So I was wondering what is the re-referencing method that you used in the case of when you quantified PLV and PLI.
Okay, in both cases, in both analysis that I did, let's say we tried different. So typically in electrocorticography, at least in Utrecht, they used a bipolar approach in order to be more focal. And but we tried also the average montage. So when I did the analysis, like I did the analysis for both, and more or less the results are in the same direction. For both, you can find the same, more or less the same results. So a bipolar and average montage.
Okay, thank you very much.
Okay. I also have a question. I mean, I don't see other hands raised right now. By the way, during the questions time, every participant can unmute himself and speak. So this is easier. So my question is, because so I understand that when you work with ECOG, it's basically, so the distinction between sensor space and source space is kind of mild. So I assume that you kind of take that the sensor space is the source space in some sense. Is that correct?
Yeah.
So when you do the virtual resection, you work on the channels directly.
Yes. Yeah.
Okay, I was wondering whether it would make sense, because I know that you can also do like inversion, like source localization from ECOG. I'm not sure it's done a lot. So I was wondering whether you tried or make good.
No, that is like one of the directions at least we were going to look, because one of the problems that you have actually is like when you have let's say the source that is a little bit deep, it's gonna spread to all your grid at the same level. So in some way, just like you have, let's say, the common source problem. And when we did this, let's say, virtual rejection, the funny thing is like most of the time, let me see if I can show you some examples. For example, here, most of the time you can see that the light blue here is way down than the real one. So we are over removing stuff. And that could be the reason, because in some way you have like a source that probably is like beneath or even far away from, let's say, the grid. And we are recording this source from every channel. So the thing is, when we are partializing it, we are removing from all the channels. So this is killing in some way all of that. So an approach with, in some way, you kind of source localize using the grid information can, in some way, keep apart this kind of contribution in a different way. So will be welcome, let's say.
Okay, but so you already tried some source localization from ECOG or
no. For that, no. For now, the only thing that we were trying was like to look at, let's say, the different delays to see if we can find a driver or not. So that we didn't try yet this kind of analysis.
Okay, thank you. I see. Very interesting anyway. Very, very, very interesting. Let me see if there are further questions. It doesn't seem to be the case. So I think we can thank you again and have a little break now.